consumable R&D. So I'm going to talk a little bit about high-strength flux cord wires that are gas shielded. These have come into the market more recently due to the increase in strength of the steels used for offshore drilling rigs, construction, shipbuilding. Basically every construction industry is going to higher strength steels. So the welding consumables are rising in strength to match that. So I chose some of the more interesting aspects of the research we've done, and mostly focusing on the effects of shielding gas on the properties and on the weldability, with a little bit of a touch into what AWS 532 allows and whether that's sufficient enough of a classification for flux cord welding. So first I'm going to go over a little bit over how shielding gas affects your properties. So the procedure for this section, we used 120 KSI strength classification electrodes with a rutile-based T1 slag system and 045 diameter, and we welded a AWS style plate at 43 kilojoules an inch on DC positive. We did change settings as we changed shielding gases. Basically, as you make these changes to shielding gas, you have to compensate voltage and wire feed speed. Otherwise, you will not get a passing weld. So basically, for the rest of this presentation, the left side is going to be higher argon blends. For properties, it goes up to 90% argon, 10% CO2, and moving to the right will be increasing amounts of CO2. So here you can see on the bottom right the amount of alloying of manganese and silicon, which is solid line, and the carbon equivalent, which is the dotted line. And so increasing the amount of CO2 in your shielding gas introduces oxygen into your weld pool. That oxygen bonds with your alloying elements and forms the slag system, which means you're getting a deterioration of alloying elements in your deposit. And where this is important is that alloying gives you strength through changes in microstructure. And so these steels are really designed in this region between upper bainite and the ferrites. And so here you can see cooling rates as the dotted lines, and that's one way to get different microstructures. But as you change alloying, you also change the position of these CCT curves. And so most of these are designed to operate in the bainitic region. It gives you good toughness while still providing high strength. And so as you change the amount of alloying, your AC3 temperature will change, as well as the position of the CCT curves as they affect the austenite and ferrite stability. And so when you start at a high argon blend and you have a bainitic microstructure, as you start to increase your CO2, you reduce the alloying elements, and that effectively moves you into the ferritic regions. So here you can see same high argon on the left, higher CO2 on the right. And at the higher amounts of argon, you're in that bainitic region, you have really high strength, or you have really high manganese and silicon, and then you move to ferrite at the lower amounts of alloying. And so this plays directly into your properties. So here's the strength of the same electrode, 120 KSI class. And this was designed for 100% CO2. And so as you increase the amount of argon in your shielding gas, you're getting increasing amounts of strength. And you can see really sharp transitions as you go through microstructural changes. So between 50% CO2 and 75-25, you see that really steep curve that corresponds to the formation of bainite. You see all the same trends you would expect normally. So as you increase in strength, your elongation goes down. You also see a decrease in CVN toughness with the higher strength shielding gas combinations. And so I wanted to talk a little bit about how we design the electrode for the customers and how that correlates to AWS 532, which is the specification on shielding gases. So I showed before that you get microstructural changes that lead to very sharp changes in properties. And the cord wires we design are for robust properties within a specific range of shielding gas. And so here are the classifications from AWS 532. They basically cover 95 to 85% argon, 85 to 75% argon, and then 75 to 50% argon. And so those are generally pretty tight ranges. But when you design an electrode, you want to be robust for what customers are actually using. And so 75-25 is really common shielding gas. Even 80-20 is really common. And you add plus or minus 5% on either side for impurities or just whatever the gas the customers get. You don't want to be on a knife edge. So we kind of design these to operate around a 70% argon to 85% argon range. And so that encompasses M21 in this case, but it also falls into M31. And for the 100% CO2, you kind of design just for 100% CO2. You don't usually get impurities or variations there. And so here's the strengths that here's the properties. And so the blue line is going to correspond to an electrode designed for 100% CO2, and the red line will correspond to an electrode designed for that 75-25 argon CO2 blend range. So here are the strengths that I showed before. So the blue line is the 100% CO2. You can see that when you weld the blue electrode in the design space it was intended for, you get really similar strengths to the mixed gas electrode that's designed for the 75-25 range. And you get really robust properties within these design spaces. But as you move outside of those, you get into these transition regions. And you see the same thing, and these transition regions encompass potentially shifts from being in spec to being out of spec for a customer. And you see the same thing when you look at CVN toughness. They're robust within the design space, but as you move outside of them, you get into microstructural changes, and those lead to very drastic effects. And so this is really important, especially when customers want to go to either a higher toughness or a higher strength, and they start to operate outside of the design space that the electrode was intended for. You get into these transition regions in the microstructure, and you might encounter a problem if you specify a 80-20 and you get some variance there, and it wasn't designed to operate in that range. So even though you might see the higher strength, you'll see a sharp decrease in toughness. And so you should be extra critical when you're assessing what your specification calls out for in terms of shielding gas, and 532 may not be sufficient. So those are kind of the effects of shielding gas on microstructure and how that affects properties. But we all know that changing shielding gas also changes weldability. And so these are bead-on-plate electrode welds. They were done with a 15-degree drag angle at all the same current and voltage. And you can see that there's a change in penetration profile as you move through these, as well as bead width. And so, again, high argon's on the left and high CO2 is on the right. And as you move to the higher amounts of argon, you see a slight decrease in the amount of bead width at the very high amounts. But really the bigger effect is that penetration drops off steeply as you get past 75-25. And so to kind of investigate, why this effect is and show it more graphically, we did some high-speed videos. So I wasn't sure if these would show up well enough, but it looks like they're okay. So the video on the left is 100% argon. The video on the right is 100% CO2. These are all at the same settings. So normally in a joint, you would compensate for the change in shielding gas by decreasing voltage, decrease arc length on your higher argon blends. But just to show what the effects are, these are the same. So, I mean, if you watch these videos, you can, when you have these two videos especially, you can see the changes. You can see it's less stable when you're in a globular transfer on the 100% CO2. As you go to 100% argon, your arc length increases. It's more of a spray transfer. It's more stable. You don't see as much spatter. But we wanted to do this for all the shielding gases, and it's really difficult to make a comparative slide that shows, all 8 shielding gas blends. So if these were videos and I press play, you would never be able to assess what's happening in each one. And so we have a method where we take a short clip. So I grabbed this little 1/10 of a second, and this is really neat. It shows 2 pieces of spatter flying out of the 100% argon. And one of them's a little oblong. You can see it flying up to the right, and it kind of spins off into 2 little pieces. It's interesting. Maybe you want to study that a little bit more. And so what we can do is take each one of those frames, and the things we're interested in are the bright spots of this weld. So you're interested in the arc, what's happening there, and you're interested in the spatter coming off of the weld. And so you assess the pictures for each frame, and you highlight the areas that are bright, and then you remove the backgrounds from those areas. So now each frame has only the region of interest highlighted. You can take all those now, and you can take your 2D frames and create a 3D reconstruction using time as a z-axis. When you compile all of that, you get a picture like this. And so you can see the 2 pieces of spatter, kind of where they're flying, what their trajectory is. But this is only 3 frames. So what if we do it for the whole thing? And then that clip that I showed you before now becomes the image on the right, where you can clearly see the trajectory, you can see how much spatter is being generated, and you can see an average of what was happening in the arc over this period of time. So this is a really neat tool, and it allows you, instead of showing 8 videos and relying on people to remember what they saw and try to make those assessments, it's a technique that allows, both in presentation style and in the lab, to make some assessments of what's happening. And so, here's the 100% argon, the 100% CO2. So the 2 videos I showed before. Before you could sort of make out what was happening, this gives you a really clear picture. Spatter is much higher on the 100% CO2. It goes in more directions. 100% argon, you can see that there's a higher arc length. Spatter's very consistently moving to the right, but there's less of it. And so when you look at all of them, you can see these trends. So they wouldn't all fit into a single line. So 100% argon's on the top left, and then moving to the right, and then down, and then to the right is increasing CO2. So these are great. They're great pictures. You can get a real clear sense of what's happening with your spatter over this period of time, and you can make quick assessment of multiple videos that would normally take hours of watching videos and taking notes. So you can sort of see here what the effect is on arc length. You can see that it's decreasing, but it gets a little fuzzy in this view because you're stacking all of the arcs from 1 second of 1,000 frames, and so they all kind of blend together. What's great is you've actually created a 3D construction. And so while we were showing this view to look at spatter, you can actually rotate your view, and now you're looking at arc length as a function of time. And so now your x-axis is time, and your z-axis is the arc length. So now when you do a comparison, you can clearly see both how high the arc length is and how stable the arc is. So the 100% argon, clearly the highest arc, and then you see a steep drop-off as you go to the 75-25, and then it kind of tapers off from 75-25 down to 100% CO2. And that 75-25 argon shielding gas blend is the transition point from a globular transfer into a spray transfer. And so that's why you see this steep rise in arc length after that point. You can also look at stability now because you can assess how much the peaks change over time. So in this 1 second, there's many ways you could assess it. You could look at just standard deviation of every frame from the average. But I chose to look at how many times the arc length changed and did the inverse of that. And so higher on the scale means more stable, more consistent, and a lower means less consistent. And so as you get to that spray transfer, you get a more stable arc, but you're imparting less force onto the base plate, which is why you're getting that less penetration. The globular transfer gives you the penetration. Spray gives you a consistent arc, but you'll see less penetration with it. And so what really matters here is if you're doing a fillet weld and you want to weld with a higher argon blend, you're going to see these higher arc lengths if you don't compensate in voltage, and that's going to allow your arc to wander more. So it becomes more difficult to actually guide your electrode into the corner of the fillet weld with the high argon blends, higher arc lengths. And so that globular transfer is really great if you need penetration in the root of a fillet. So, again, the takeaways I hope you got from this are that shielding gas is just as critical in your selection process as your electrode selection. It drives your alloying drives your microstructure, and your microstructure drives your properties. And you can't ignore the fact that changing your shielding gas is going to change weldability. And if you talk to any welder, they'll tell you what their favorite shielding gas blend is for that reason. The specificity of A532 may not be sufficient for some applications, especially as you start leaving the design space that's intended for an electrode. And lastly, what the effects of shielding gases are through the use of these high-speed videos and our novel approach of how to make comparative analysis from that. So I'll take any questions.